Thank you for joining us this morning for our webinar on hands-on with Cscan Protocol. The presentation itself is roughly about 20 minutes, and feel free to throw any questions into the chat and we'll get to them at the end.
Welcome to today's tutorial. Let's get started. Let's have a look at the agenda for today. First, we'll do a quick review of Cscan. So we'll look at what is Cscan, when would you use Cscan versus Ethernet, and how does Cscan global data work. Those topics were all covered in our previous webinar on Cscan, which you can find on the Horner website. Then we'll go through the different Cscan configuration and function blocks that are available in Cscape. Then we'll show an example application utilizing Cscan. We'll have a demonstration and we'll finish with a Q&A session. First, let's do our quick review of Cscan. So first, what is Cscan? Cscan stands for Control Station CAN. It's a Horner network proprietary in nature that's based on the CAN chip. The CAN chip, and therefore Cscan, is very robust and reliable in harsh environments. Also, CAN and Cscan are typically used in a daisy-chained peer-to-peer type fashion. One of the nice things about Cscan, in contrast to Ethernet, is that device power is included on the network. So there's either 12 volts or 24 volts. It's also designed by Horner to be easy to use. From a functionality standpoint, it's often used to expand the I/O in an OCS. It's also often used for OCS to OCS communications, which is what we'll focus on today. It can also be used for what's called single point of connect programming. So if you have multiple OCSs interconnected over Cscan and you connect to any one of those OCSs from Cscape, you can effectively program any of those OCS devices to that single connection. So when would you use Cscan instead of Ethernet? So when you want a daisy chain type architecture where you would prefer to connect units linearly instead of in a star or home run type configuration, is where Cscan has a nice advantage. Another example is when you want a single cable solution for your network, as well as your device power. One useful thing with Cscan is you do not need any extra network infrastructure, such as Ethernet switches or Ethernet routers. So therefore there's less hardware required. If you have an application that's very harsh electrically or environmentally, Cscan is a good choice. Cscan is also a good choice if the amount of data you're exchanging between devices is modest. If you have hundreds of words of data that need to be shared between devices, Ethernet is a better choice in those particular applications. So how does Cscan work? Cscan takes full advantage of the peer-to-peer capabilities of the CAN chip. Another benefit of the peer-to-peer is that any Cscan device can talk to the network when it has data to communicate and the network is available, so it doesn't have to wait for another node to tell it to communicate. The way Cscan handles exchanging data between OCS units is based on what's called global data. So each Cscan device ID is assigned global data, both digital, which is called QG, and analog, which is called AQG. So that node can then broadcast to the network. Every OCS on the network has access to all the global data broadcast by any node, and each node has a limited amount of data that they can broadcast to the network. Let's talk about Cscan global data going out to the network. As mentioned, each OCS node ID can have both digital and analog data that it broadcasts. Each node ID can handle 64 QGs or digital bits and 32 AQGs or analog words. If the OCS needs more data than that to broadcast to the network, you can assign multiple consecutive node IDs to that OCS. You use a NetPut function block in your program to broadcast the global data to the network, and anytime the network is available, the OCS can choose to broadcast it to the network. That global data is typically broadcast 4 words at a time. Also note that every OCS can broadcast by default 1 CAN message per scan, but you can increase that. Next, we'll look at global data in from the network. With Cscan, every OCS in the background automatically sees any global data that's flying around on the network and makes a copy of it into its internal memory or its RAM. And then each OCS can use NetGet function blocks to act like a move block. That function grabs data from the internal RAM map and copies it to a variable that can be used in the OCS program. No traffic is generated by a NetGet, unlike a NetPut function block. Let's look at how that global data exchange works through a graphical representation. So let's say we have 3 OCSs on a network. Node 1 executes a NetPut instruction, and then that global data gets broadcast to the network. Then, automatically in the background, all the other OCSs on the network copy that data into their local RAM, whether they're going to use that data or not. When Node 2 needs to transmit data to the network, the same thing happens. It broadcasts global data to the network, and all the other OCSs on the CAN network copy it to their local memory, whether they're going to use it or not. The same thing happens with number 3. Every OCS can transmit global data, and every other OCS will make a copy of that information into its local memory. Again, NetPuts always generate traffic because an actual message is being sent. And then to take advantage of the global data broadcast by the other controllers, you can use the NetGet instructions to copy that data from RAM locally into local variables where you can use it in your program. Again, since a NetGet is just a data copy, there is no bandwidth being used. In a typical application, not all the network data is relevant to every OCS. NetGets are only used for the data that's relevant to each individual OCS. Next, we'll talk about configuring Cscan. We'll start with the network configuration dialog box for Cscan, and then we'll look at different function blocks you can use for exchanging data between controllers. Here are some highlights I want to handle on the Cscan network configuration. First, you only need to check the network required checkbox if you're going to be using the Cscan network. What that will do is if the Cscan network is not operating properly and therefore the network OK status is off, then the OK LED for the OCS that you can see from the system menu will then turn off when that network goes down. Also, there's a network optimized checkbox, and you always want to have that checked. That ensures that a full 4 words of global data are broadcast with every CAN message. As mentioned previously, you can assign multiple consecutive IDs to an OCS if you need more than 64 bits and 32 words of global data to be broadcast by that particular node. The dialog section is where you can assign multiple consecutive IDs. Lastly, we have max packets per scan. By default, the OCS will broadcast a maximum of 1 CAN message per scan, which means 4 words. If you want the ability for the OCS to send multiple CAN messages per scan, then you can increase that number. Let's start with the NetPut instruction. That instruction is what broadcasts your global data. It's typically used on a change of state basis. That means the OCS will only broadcast the global data whenever it changes, which will manage bandwidth efficiently. If you have analog data, for example, that you would rather broadcast on a periodic basis, you can do that as well. It just means that you need to create some logic in your application to trigger that message and use that as the digital enable for the function block. I'll have examples of that in our demonstration later. You must also be careful not to flood the network with extra traffic. Next, we have the NetGet instruction, and that is basically a data move where it grabs data internally from RAM and it's going to place it like a move block would into an internal variable. Again, NetGet instructions do not generate network traffic because they're just a copy from local memory. Then we have a few more important instructions such as the NetPut heartbeat and the NetGet heartbeat. These are used so that different OCSs on the network can pay attention and validate that another OCS that is important to it is active on the network. These send out heartbeat messages periodically, so the receiver of the message expects to receive a heartbeat before a timer runs out. If the receiver fails to receive that, it knows the sender is not active on the network or a node is down, and therefore you can take corrective action on any data that you're receiving from that other node, as it could be an old copy, for example. The next instruction we'll look at is the SetCanID instruction. Normally the CAN address or the node address or the node ID is set from the system menu. However, with this SetCanID instruction, it gives you the ability to, in the logic, set the CAN address of your OCS. You could have a CAN address data field on a screen that is the source of that CAN ID, or it could be some algorithm in your logic to determine what the local OCS should be in terms of its local network ID if you wanted to do that automatically. So next we'll look at an example application that I've set up. In this example we have a manufacturing environment with multiple identical modular stations. Parts are moved from station to station, and each station is performing a very similar progressive operation. The same OCS can be used to control every station, and the same program can reside in each OCS that's identical. So you have the flexibility to move these stations around physically and re-interconnect them. And because they're all running the same program, you don't have to reprogram anything. Once again, in my example, every OCS program is identical. Each OCS has what's called a station ID that is set from the touchscreen. The idea is that this station's IDs are sequential, in my example from 1 to 4, although there's no reason you should have to limit it to 4, and the station ID will be used for the CAN ID. In this kind of example application, every OCS performs a load in to its station whenever it's empty and the previous station is ready to send a part to it. Then subsequently each OCS sends on to the next station the part that it's been working on as soon as the next station is empty, and we're done with the part when it comes to processing on our current station. Then all 4 stations in my example receive operational parameters from a centralized OCS, which is an ESXLW in my case, which has a large screen for displaying the parameters. Now here's an outline of what we need to set up to make that work. Because I've decided to allow the application to be set up from the touchscreen in terms of its CAN ID, then I'm going to use a SetCanID instruction. Every OCS is going to send a heartbeat to the network, so we'll use that NetPut heartbeat instruction. We'll also monitor the heartbeat from the other OCSs that we care about. In this application, each OCS cares about the station that's right before it and the station that's right after it. So those are the ones that it's going to pay attention to using a NetGet heartbeat instruction. Every OCS is going to use a NetPut instruction to broadcast data to the network. Then every OCS is going to use NetGet instructions to set up local variables for the data from the coordinator and the data from the previous and the next OCS in line. Now let's begin our demo, where we'll look at how to set up that example application in Cscape. Here's my application. In my example, I said that we'll set the SetCanID not from the system menu, but from the touchscreen. Therefore, I need to use this SetCanID function block, and the variable that's being fed into it is populated from a data object on the touchscreen. As I mentioned earlier, every OCS cares about the station ID before it and the station ID after it. So we need to calculate based on our own station ID what the previous station's ID is, as well as what the next station's ID is. For that, we'll simply subtract 1 or add 1 to the ID. Then we have special cases for the first station in line and the last station in line. For the first in line, it'll receive some extra data from the coordinator OCS. The same goes for the last station in line. For the next step, I have a section of logic that deals with Cscan heartbeats. Again, every OCS is running the same program, so that means every OCS is broadcasting a heartbeat every 500 milliseconds. I'm using this NetPut heartbeat function to generate the heartbeat every 500 milliseconds. Then I have 3 get heartbeat instructions. So here I'm checking the heartbeat for the coordinator, as well as the heartbeat for the previous station and the next station, based on what I've calculated those IDs to be, which is all I'm worried about here. Then when I'm configuring this NetGet heartbeat instruction, even though every OCS is generating a heartbeat every 500 milliseconds, I'm only going to have a timeout of 1000 milliseconds for the heartbeat to be late. Then if everything's working as it should, I have an OK status bit for every OCS that I care about. Those are for the coordinator, then the previous station, and the next station. Next, let's look at the Cscan out section. In this section, every OCS is taking local variables and copying them to an array, which is broadcasted to the network. Remember, when you broadcast global data, you have both digital or bit type data, as well as analog or word type data. So in these 4 rungs, I'm taking 4 of my bit type variables and copying them over one at a time to 4 locations in an array, which are then broadcast using this NetPut function. When you use a NetPut, it's broadcast 1 word at a time. So you cannot broadcast less than 1 word of bit type data using the NetPut. You'll have a minimum of 16 bits that are going to be broadcast. In this case, we only had 4 meaningful bits in our example. So that's all I've assigned to this array. Then down here we had 2 pieces of word type data, an actual temperature and an actual time that are being broadcast as word status information to the network. Now in this case, I'm going to send this data to the network once per second. I have a trigger bit here that is one shot that turns on once per second and triggers the NetPut for this word type status information. So every OCS in our example is going to be broadcasting data to the network. That data is automatically being placed in RAM by every OCS on the network, and then it takes NetGet instructions to be used in your local program to take the received data and copy it over to a local variable that you can use in your program. Next, I'll go to the CScanID sections here, of which I have two. This is a section of code where we'll use NetGet instructions to copy data from local memory, which was broadcast by other OCSs. Using this NetGet, we're copying one word of data from the previous station and its digital data, and we're copying it into a local array. For the OCS that's the previous station to us, we only care about one bit that says that previous station is ready to send us another part. Then I've mapped the global data we received from this function block over to a local variable called previous ready to send. Similarly, we have another NetGet function block getting data from the next station in line, and the information we want here is then being copied to a local variable called next station is empty. So that's the digital data we're exchanging from OCS to OCS as parts transition from one to the next. Then we have a section here called CScanID from the coordinator. In this case, first we'll receive in digital data, and then we'll receive in analog data. Then we'll copy over the bits from the received digital global data over to variables for our local program that tells us that the system's in auto mode. Then for the first or the last station in line, we'll get some information from the coordinator to pass us from a loader component and a stacker component. So that's digital data being passed to each OCS by the coordinator over Cscan. We're also receiving in temperature and time set points for these machines as word type data. Each station has its own time and temperature set point that it can receive from the coordinator, and the coordinator is sending that out as one block of global data. And then it's up to each individual OCS or station to extract the appropriate set points for that station. We have some logic here where we're calculating an offset and using an indirect move so that we can copy the two words of set point information needed by this local station depending on its ID. And we're moving that information into a local variable. So that's the logic to receive data in over Cscan from the coordinator. So let's look at all that now on the OCS. So here you can see I have my coordinator on the left, which is the EXLW. Then I have two XL4s which are acting as the controllers for each station. One of the things the coordinator sends to all the OCSs is whether the system is in automatic mode or not. So when I switch automatic mode here from the coordinator, you can see on every individual station that that bit is important and therefore it's being received by every station. That data is then mapped over to a local variable on every OCS. Looking at my stations, I have the ability by using this data field to change the ID of that local station. You can see that if I'm ready to send a part to the next station, that status is reflected in the next station. Let's say that first we want to load a part into the first station. That must come from the loader. Now, since we had a part come in from the loader that we're in the process of loading, we're no longer empty. The next station is empty, and when we want to send that part on, we start sending it and it starts receiving it. Then there's set point type data from the coordinator. So if I go into my temperature set point for station 1 and I change that to a different value, you can see that it shows up here on this station. It doesn't show up here because that's not the intended set point for that station. So that's the logic I use for the indirect move to calculate where in that global data my set points are located. That concludes our demonstration. Thank you for joining us for today's tutorial, and the Q&A session will begin shortly.
Okay, I'm not seeing any questions so far, so I'll take us across. So we do have another webinar on Cscan next week, which is tied in with Smart Rail IO. Following that, we are at the SPS show, so we are not there the following week. And then we'll be back with Ethernet Global Data the week after. So just to bear in mind, we won't be here the week after Smart Rail. Anything else? Okay, just a thank you note for the webinar, no problem. I'm glad to have you with us today. Yeah, other than that, all the past webinars are there as usual, and they'll get uploaded within a day or two of the webinar if you want to go back and pick apart any few bits that you need. Other than that, we hope to see you again next week. Thank you.